We have our first tool in our time value of money toolbox, right? The future value of a single cash flow formula. Present value times 1 plus the interest rate raised to n being the time. So this is lots of things will build on top of this, all right, formula. So this is key, very important for us. So let's spend some time talking about this and let's see how powerful this is, all right? One thing I want to emphasize is this n in the exponential term. This is the source of that exponential growth. What people call magic of compounding is that you can end up with a huge sum of money. It follows from that n being the exponential term. So exponential growth, right? Very powerful, very, very important force. So what it will look like is if you were to draw, for example, what happens to future value of, say, a certain amount today. So that's our PV over time. So say n. So as n grows, let's say from 1 year to more, and you have a certain amount today in the deposit in the account, for example. So it will be a larger amount in 1 year, and it will be larger in 2 years, it will be larger in 3 years, following this formula. But because of this exponential growth, this is not going to be a linear relationship. We're not going to have just the same pace of increase with each year. What we're going to have, because earlier interest is earning interest itself, is we are going to have this exponential growth in future value. So it's going to, instead of linear, it will look more like something like this, okay? And the larger the n, you can see the greater the impact, and you're really sloping up, and the amount that will increase each year will be much, much greater in the future than in the first few years. So if you have a large n number, this is going to make a huge difference. But the other thing is I, of course. The greater the I, the greater the force behind exponential growth. So we're going to have a huge increase. So that's why people say start investing in the stock market early, for example. And so that you have something like 30, 40, 50 years of horizon before your retirement, or a few years after your retirement as well. So investing period where you can earn, say, something like an average annual rate of, say, 8%, 9%, 10% per year for 30, 40 years. You really take advantage of that exponential growth and the magic of compounding. So this is what people refer to as the magic of compounding. Not linear, but this exponential growth. Okay, so it all comes from this exponential term. Very, very important. All right, what else? What else is, so far we've talked about like a bank account, simple interest rate being earned, or compound interest being earned, but we are doing time value of money for bigger reasons. All right, and in part, so this formula will apply to many different settings. It's not limited to savings account, as I already gave the example of stock market investing, for example. But basically, this can be any growth rate, right? A little bit of a darker example, you can think of it as the spread of a disease. That can also be exponential growth unless you take certain measures, right? So how many people will catch the disease, for example, COVID-19, starting number, growth rate, how many years, or the time period over which that growth will happen. So similarly, so this will apply to any single amount today, growing at a certain rate, fixed rate, over a certain number of years, the resulting number. So this formula applies. What else? But what we are really interested in finance a lot is what is the PV, present value of future cash flows, right? So we often will need to work with this in reverse, okay? So for example, if someone offered you $1,000 in 1 year, how much is it worth to you today, right? And we are interested in that because that's what valuation is. Finance is very interested in valuation, stock valuation, bond valuation, asset valuation, right? And valuation is trying to figure out what is the value today, the PV of things, of what? Cash flows in the future, right? So the value of an asset is the present value of all the different future cash flows that you expect that asset to generate in the future. That's what the value of a stock is, for example. It is core. That's fundamental valuation. Okay, so we really want this PV. So what do? Very simple. If you're talking about the present value of a single cash flow in the future, we just do simple algebra. We just need to leave PV alone, and it will work, right? PV, divide both sides by 1 plus I raised to n, and we're going to have PV equals FV divided by 1 plus I raised to n. That's all it is. And then you plug it in, divide by 1 plus I raised to n, that gives the present value today. So for example, when you encounter a question like, you need a certain amount of money in, say, 5 years, and let's say you're going to deposit some amount today, earning in an account earning I for n years, how much do you need to deposit today, right? So you know your target, you want to know how much you would need to deposit today, so we need to use this present value formula. Or you have an asset that you expect will generate a single cash flow of this much in this many years, how much is it worth today? Again, that's finding the present value. But that's not it, we can do a whole lot more. So there are 4 variables here, right? So we figured out how to find FV, we figured out how to find PV. We can do the same for interest rate. So for example, you know your starting point, you know your target amount, so you know FV, PV and FV, and you know how many years, so that's your investment horizon. What type of interest rate do you need, right? So for example, you need to save a certain amount by a certain number of years. What type of an interest rate do you need in that account to be able to reach your target, right? So that's simple algebra as well. We just need to leave I alone. That's a little bit more involved compared to PV. We need to bring PV to the left-hand side, FV divided by PV. And then we need to take the nth root of both sides, minus 1. So eventually what we're going to end up with after some algebraic manipulation is we are going to end up with I equals FV divided by PV raised to 1 over n, right? So that's the nth root, right? Minus 1. So when we know this PV, FV, and n, the interest rate that satisfies this condition will be given by this formula. And the last piece of the puzzle is n. So you know again your starting point and your ending point, PV and FV. And let's say you know what type of opportunity you will invest your money in, say a bank account or bonds or stock market. So you have an expectation about what the growth rate will be. And you're wondering, how many years will it take to reach my target? So now we need to leave n alone, but this is an exponential term. So to leave it alone, it's a little bit more involved, and we're going to have to use natural logarithms to solve for n. So the formula is going to be, in the numerator, we're going to have the natural logarithm, so ln of FV divided by PV, and divided by, again, the natural logarithm, so ln of 1 plus I. Okay? And if you plug the numbers in, crunch the numbers, we can find how long it will take to grow a certain number today to a certain number in the future in an opportunity that's earning I% per year. Okay? So these all follow from that, our first tool in our toolbox. So now our toolbox is growing.